In class, I usually bring in some newspaper articles which talk about statistics and abuse statistics. And the most abusive thing in statistics is the use of correlation, the thing we're going to talk about today. In about 10 seconds, you will know more about correlation than half the people who talk about correlation in the newspapers. Here's the 10 seconds. Correlation is not cause and effect. Correlation is not cause and effect. Now I'll show you why, knowing that, you know more than half the people. Let's imagine some cause having two effects. That's not too hard. One cause having two effects. I'm going to give an example so we can understand it. Now, I don't want to offend anyone, but I'm making an example that's way out, so there'll be no confusion in our heads. We'll know exactly what's right and what's wrong. And here's the example. I'll list the year, the population of the United States, the number of Baptist ministers ordained, and the rate of alcoholism in the United States. The idea here is that during the years 1950 to 1990, the population in the United States grew. These are rounded numbers. Population in the United States grew. And because the population got larger, the number of ministers also got larger. And I've made the numbers so that they match up so well that you can actually see the relationship there, that the number of the population caused the ministers. Of course, the ministers didn't cause the population. More people, more ministers get ordained. More people, we need more ministers. More people, we need more ministers. So the population growth caused there to be more ministers ordained. Now, forget the ministers. Forget them. Population got bigger, things got worse, we got alcoholism, 25% rate of alcoholism. Larger population, higher rate of alcohol. Larger population, higher rate of alcohol. As the population got more and more, the alcoholism rate went up. Now, I've made the numbers exactly the same here so you can see the relationship without any trouble at all. So we see that population can cause alcoholism to go up, and population can cause ministers to be more. Now, let's take it for granted that the population is what caused these two. You might have some arguments about saying something else causes alcoholism, but let's say it's population and not worry too much about other things. Well, that's fine, except that in the newspapers, what you will find is that nobody's going to talk about the population. They're just going to talk about things like this: the number of Baptist ministers ordained and the rate of alcoholism. And they're going to say, look at the relationship here. Look at that relationship. Therefore, Baptist ministers ordained is causing alcoholism. They are going to try and show you a cause and effect relationship because the numbers appear to be related. In fact, what's going on is, well, if you plot it, let's plot that data. Baptist ministers ordained, rate of alcoholism, a perfect straight line. Absolutely perfect straight line. Of course, I didn't draw a perfect straight line, but the relationship there looks like a straight line. However, do not draw that line, because correlation is when two variables seem to vary together. Here is it, seem. They are actually, let's be honest, they are varying together. They're getting bigger and bigger. There's Baptist ministers and alcoholism. They seem to vary together. They do vary together. One gets bigger, the other one appears to get bigger. However, that's not a cause and effect relationship. Not all relationships are cause and effect relationships. Why must a relationship be a cause and effect? It's true. If there was a cause and effect relationship, if one thing caused another, and you plot them, you could see the points going on a straight line. You'd be able to say, hey, there's a linear regression here, there's a cause and effect relationship, I can see it. There is a straight line, there's a correlation. If I have a cause and effect relationship, I have a seemingly varying things varying together. Therefore, I have a correlation. Correlation says that things appear to vary together. If they appear to vary together, they have a correlation. Cause and effect produces a correlation. People work it backwards and say, I see a correlation, therefore it must be a cause and effect. There's nothing that says you have to have a cause and effect. We saw an example. Baptist ministers, alcoholism, both caused by something else, population growth. Yet Baptist ministers and alcoholism were highly correlated, but they're not cause and effect. You cannot say that if you ordain more ministers, there's going to be a higher rate of alcoholism. You also can't say if you outlaw alcoholism, there'll be no more ministers. It doesn't work that way. There's no cause and effect between alcoholism and number of ministers ordained. And that's obvious. What's not so obvious is when you have other things which appear to be correlated, and people see the correlation and draw a graph of it and say, therefore, this causes that. And we believe them, but we shouldn't. Unless you can show a cause and effect relationship, unless you can do an experiment where you vary one thing and the other consequence occurs. If I have a dial and I turn my dial and the light gets brighter as I turn my dial, I have a cause and effect relationship. If I drink beer and I get drunk, I have a cause and effect relationship. But because I'm drunk and I happen to have drank beer doesn't produce a cause and effect relationship, because I might be drunk and I happen to be driving my car. Driving cars does not produce intoxication. Okay? Do not confuse correlation with cause and effect. Cause and effect produces correlation. Correlation is not necessarily a cause and effect. I know it's a tricky concept. Think about it, you'll get it. How do you estimate correlation? Well, you'll only need it for homework. You won't have to remember it. We estimate it with what's called the product moment correlation. The measure of correlation is the product moment correlation, and it's a formula very similar to the one we've already seen. You've got paired data, x's and y's, subtract off their average, then multiply them together, sum them up. Now, instead of just dividing by, last time we just divided by this, now what I want you to do is to take x minus x bar squared, sum them up, take y minus y bar squared, sum them up, and take the square root of it. That will be the measure of correlation. Now you can't tell by looking at that, but I'll tell you that the correlation, called the correlation coefficient or the product moment correlation coefficient or the product moment correlation, the product moment correlation cannot be bigger than +1 or less than -1, and varies, can take any number, given any x's and y's in the world, can take numbers between -1 and +1, but not less than -1 nor more than +1. So correlation, any number between -1 and +1 is a legitimate correlation. Now, what happens when you see data like this? You see data, it looks like this. They're seem to be related, well then they're correlated. If they fall on a perfect straight line like this, the correlation is 1. Perfect positive correlation. They go in a positive direction. As one goes, as this gets bigger, this gets bigger. You know what a positive slope is. There's a positive direction like this. R is +1. If the data is near the straight line, but bouncing around it a little, so that you get a little cigar-shaped bunch of data, then R might be 0.8, say. And as it gets a little bit bigger, R might be 0.4, say. And as the thing gets bigger and bigger, the data bounces around like that, R might be 0.2. By the time you reach the data, which is in a circle, and you can't really tell any relationship between x and y, you could draw any line through it you like, then R is 0. When you have a relationship that just doesn't look like it's falling in a straight line, R is 0. As the relationship gets tighter and tighter towards towards this line, the r gets bigger and bigger until eventually when you hit a perfect straight line, r is +1. That's what the data looks like for the r, the correlation coefficient, to be between 0 and 1. Now we have negative correlation. In negative correlation, the straight line looks this way. R is -1 for this. This is a perfect straight line in the negative direction. And as one gets bigger, the other gets smaller. As one of these variables gets bigger, the other gets smaller. I'm not saying there's no cause and effect. It's just one variable bigger. This is the y variable. This is the x variable. As y gets bigger, x gets smaller. As x gets bigger, y gets smaller. See? As y gets bigger, here's y. As y gets smaller, it's going down. Y is going down. X is getting bigger. As x is getting bigger, y is getting smaller. Right? -1, perfect. But if the data is not on the line perfectly but misses it, then r might be some lower number, say 0.8. And as the data gets further and further from the line, gets more and more spread out, r gets to be smaller, say 0.5. And maybe like that, r might be 0.3. By the time you reach the data bouncing around in here where you can't tell what the line looks like, whether you draw it that way or this way, then r will be 0 again. So r, if the data looks like it lines up like that, r will be positive. If the data looks like it lines up like that, r will be negative. And the closer the data is to the line, the stronger the correlation. R is either more positively close to 1 or more negatively close to -1. Okay? Now, notice that both x and y are effects, and neither causes the other, unless you happen to be in a cause and effect situation. But generally speaking, if you're not in a cause and effect situation, just a correlation situation, then both x and y are effects. And there's a trick question I've seen on exams. On which axes do you put the cause in correlation? Well, it's a trick question because there is no cause in correlation. So you put it on neither axis because you don't know what it is. If someone said, what axis do you put the effect in correlation? Well, it's either. The answer to that would be either axes because they're both effects. So I can put the effect on either axis in correlation. Okay, let's take an example. Weight and height. Weight and height, believe it or not, are correlated. And people will show you a chart of weight and height and say, you see, let's draw a line. Now I can predict someone's height from their weight because there's a cause and effect relationship here. Anytime you draw a line and you go like this, you are assuming a cause and effect relationship. You are drawing a regression line. Do not draw lines on a correlation plot because that makes people want to do this. They do this, they're making a mistake because you cannot talk about someone's height because of his weight. They only appear to be, but that will not make. Okay, my grandmother, let's take Johnny. Johnny's grandmother used to say, Johnny, eat up. You'll grow tall and be a basketball player. So Johnny ate up. He ate everything all the time. Johnny is now a linebacker on the Tech football team. He never did play basketball. He's 5'8" and weighs 296 pounds. Okay? If you eat a lot, you'll get fat. You won't get tall. Someone's weight does not improve their height. If someone weighs a lot, that doesn't mean they're tall. If someone weighs a little, it doesn't mean they're short. Okay? So here's something to remember. Fattening someone up will not increase his height because weight and height are correlated. Correlated, not cause and effect. Okay? Now, I've also seen people draw the chart this way. Height and weight. That sort of implies height is the cause and weight is the response, is the effect. And they draw a line. They say, oh, you see? Well, I'm here to tell you, do not draw that line because you will be tempted to predict weight from height. And weight and height are correlated. They are not cause and effect. Let me say, stretching someone will not increase his weight. You can put them on the rack and stretch them all you want, but you will not make them any heavier if you do that. Of course, if you cut off their head, I agree they will lose weight. But other than that, stretching or squishing someone down will not change his weight. Now, it's easy to obtain correlations. In statistics, what we do is use, Minitab again. We just say correlate the data, C1. I put the data in C1 and C2, just say correlation, and it says correlation of C1 and C2 is 0.935. That's highly correlated. However, even that higher correlation does not imply a cause and effect. Okay, what's the most important thing you can learn about correlation? Is it's not necessarily cause and effect. And correlation does not imply a cause and effect. And when you read newspaper articles, they will correlate. They will say the correlation between these two variables was 0.87, therefore, and then they go ahead and try and convince you of something, one thing causing another. And most of the studies you see are those studies. I question them. I want to see what's going on. I do not know because they don't give me the details. They keep telling you that if you have eat oat bran and you won't have a heart attack. Well, does that mean they fed people oat bran and then they watched whether they got a heart attack or not? Or do they just make a question survey? If you had a heart attack, did you eat oat bran? It's like cigarette smoking and cancer. When it first came out, first people were saying cigarette smoking causes cancer. The studies that were made were studies that looked at people who had cancer in the hospital and said, do you smoke? And they found a lot of smokers among the cancer people. Well, now, I don't smoke, and I was always convinced that smoking causes cancer, but this data made me sick because there's no way of knowing whether smoking caused the cancer or the cancer caused the smoking. It could be that you have, say, a gene which is going to give you cancer. Okay, I'm going to get cancer because I have this gene. Well, that same gene may give me a desire to smoke. So I've smoked because I have the gene, and I get cancer because I have the gene, but smoking doesn't cause the cancer, nor does cancer cause the smoking. They're both caused by something else. That kind of survey could not establish a cause and effect. However, then they gave dogs cigarettes and made them smoke it, and the dogs that smoked got cancer, and those that didn't get cancer. And that's a causal relationship between smoking and cancer. You can actually show that smoking causes cancer. And when you can do that, you have a cause and effect relationship. Okay? Without that, it's only a correlated relationship, which doesn't prove anything. I hope you learned something. Bye-bye.